In this video, we're going to look at the force on a current carrying conductor. Now, when we say force on a current carrying conductor, we actually mean when placed in a magnetic field. So a simple circuit diagram or a simple diagram for the whole setup will look like this. So we've got our current carrying wire and we are putting it in a magnetic field. So we will have a north to south magnetic field, and it's usually represented by something like this, where we've got a piece of apparatus called a yoke, which is like a U-shaped piece of metal, and then the magnets will be put on a mass balance so that we can see what the change in mass is and therefore see what the force is. So if we zoom in on the magnetic field, we know that the magnetic field goes north to south, and importantly, the current goes positive to negative. So we're talking about conventional current here, and that's really important because we know that the electrons are actually flowing the other way, but we always talk about conventional current. As to what direction the force will be, we need to use Fleming's left-hand rule, and I've made another video on this. So we have our thumb is the force or the motion, the first finger is the field, and the second finger is the current. So we've got field going this direction, current. So the force in this example here will be up. So what is the size of this force? Well, it's given by the equation F equals BIL. This is given on the formula sheet, but usually students remember this because it spells BIL, and that's obviously very easy for students to remember. So F stands for force, and that's in newtons. L stands for length in meters. I stands for current in amperes. And B stands for, formally, it's magnetic flux density. Now, I'll explain what this means in a second, but this essentially is analogous to magnetic field strength. And it's at GCSE perfectly acceptable to call it magnetic field strength. But what do we actually mean by magnetic flux density? Well, firstly, it's measured in a unit called Tesla, which is named after Nikola Tesla, and students will of course have heard of the company Tesla now. So again, they usually do actually remember this in my experience because Tesla is in the news all the time. But what do we mean by this concept flux density? Well, if we think about a bar magnet, if we think about the lines that we draw on it, these are the magnetic field lines, and these lines represent force. That's why we draw them. And the more lines there are in a given area, the stronger the force. All right. So if we pick a given area here and compare it to a given area here, right, we can see that there are many more lines in the same area here than here. So the field is obviously stronger here. Or we could say the density of lines here is greater. Now, density, of course, is mass over volume, and this is a two-dimensional shape. But what this really is a two-dimensional representation of three-dimensional space. So actually, density is completely fine here because we are talking about a volume in space. So this is one way of tackling what this means, and usually is enough. If you want to go into a little bit more detail, we can actually really start to explain what we mean by flux. So in everyday life, if something is in a state of flux, we'd say it's in a state of motion, and that helps us to understand what flux means. So a really good example for this is if you imagine it's raining, and let's draw some raindrops that are evenly spread out. And then if we consider a surface, flux is purely the amount of raindrops or the amount of stuff that will pass through a given surface. So the flux here would be 5 raindrops, or 5 raindrops per second, or whatever. Usually it's per something. So with magnetic field, it's obviously I'm just going to pause the video here a second. Sorry about that. So we were saying that the flux here would be 5 raindrops, or 5 raindrops per second. So now what I want you to do is imagine that we're going to tilt this surface. So it's going to be the same area, but we're going to tilt it at some angle. What is the flux through the surface now? Well, you can see this raindrop misses and this raindrop misses. So the flux will be 3 raindrops per second. And again, if we tilted it even further, what would happen now? This raindrop misses and this raindrop misses. So the flux would be 1 raindrop per second. So this concept becomes really important when we start to look at motors, or even the force on wires. If it's a coil of wire that has some area like this, then the angle that coil is to the magnetic field becomes really important. And if the coil is aligned this way and the magnetic field is coming down the way these arrows are coming down, then you can see there's virtually going to be no force on it. Whereas if the coil is aligned this way, then it's going to see the full magnetic field, and therefore the flux is going to be greatest. So with higher ability sets, I would certainly talk about this, but this level of understanding is certainly not needed on the exam. But I think it does help a lot of students, particularly when you talk about motors, to really understand what's going on. So let's look at a couple of exam questions. So a common one is just to explain the situation. So when a current passes through the wire, and we're talking about this situation here, that will usually be a diagram, the balance reading increases. Explain why. Now, the way I've drawn this diagram, we've already said the force is up. So actually, there should be a slight change here. We should reverse the direction of current, and then the reading will increase. So this is a fairly standard answer, and we should really run this home with students. So the current in the wire creates a magnetic field around the wire. So this is one of our basic principles, that currents create magnetic fields. So we use the right-hand rule for this, and the magnetic field is round like this. So this magnetic field, I'm just going to use B field for shorter version, but we should probably encourage students to write it properly. This B field interacts with the permanent magnetic field, okay, and then Fleming's left-hand rule tells us the direction of the force, which in this case, now I've corrected my diagram, is down. And the last step, which is potentially the trickiest, is that by Newton's third law, there is a force on the magnets downwards. So the balance reading increases. Now, I've actually made a really stupid mistake here. I've fallen for the trap which everyone falls for, which is I've completely forgotten Newton's third law. So I was completely correct the first time, actually, when I said this, that we should actually have the current going this way, because then the force on the wire is up, and by Newton's third law, the force on the balance goes down. So my first situation actually was correct, and my correction that I've got wrong would actually mean the reading on the balance would decrease. So it goes to show that it's really easy to make this mistake, because we're linking something from the forces unit into electromagnetism, which is where it actually does get complicated. So these three are really standard and really easy. You can basically write these with no thought. This fourth bullet point here does require thought, and it requires a deep level of understanding that is actually quite easy to get wrong. Right, let's look at one more question. So I've shortened the question itself, but this is fairly typical now. If the length of the wire in the magnetic field, so this has to be in the magnetic field. So importantly, this section of wire won't feel a force because they're not in the magnetic field. If the current is 800 milliamps and the reading on the balance is 1.2 grams, what is the magnetic flux density? So first step, write down the equation, which, like I said, is on the formula sheet. Now, I've made this as hard as I can. You probably won't get a question quite as tricky as this, but I've seen individually each of these parts in questions before. So firstly, we need to make sure we're working in the correct units. So our length we want in meters. So we don't want in millimeters. We want to turn it into meters. So that's 0.05 meters by dividing by 1,000. Our current, we don't want it in milliamps. We want it in amps. So we want to divide by 1,000 to get it in amps. B is what we're trying to work out, and force. We haven't been given force. We've been given mass. And again, we don't want mass in grams, we want it in kilograms, so we divide by 1,000 to get it into kilograms. So now we need to say that force is actually mass times gravity, so it's 0.0012 kilograms times by 9.8 newtons per kilogram, and that will give us our force. And then we need to say that magnetic flux density is force divided by current times length. So some students are completely capable of doing this rearrangement. Other students, you might actually just want to get them to write down the numbers in the equation and then rearrange it with numbers, because a lot of students find this easier. So we could just write it down like this, equals B. Sometimes even a question mark. Even higher tier students, sometimes just putting a question mark instead of the B actually makes it easier for them. And GCSE examiners aren't going to mind this. Times the current, times by the length. And then again, I'm aiming at the kind of bottom end of higher tier here with this method. Equals our question mark times by 0.004, and then our question mark, which equals our magnetic flux density. This divided by this is 0.294 Tesla. However, better students will be able to rearrange it, and this is obviously better to rearrange it. So I should probably make clear that all of this is higher tier for AQA, which does make our lives a little bit easier because these are complicated concepts.